All right. So today we have Jay Gu tell us about rational Q systems and linear quiver gauge theories. Take it away.
Okay, thank you, Raj. Thank you, Julius, for inviting me, and also thank Marcus for the suggestion. So this work is the talk is based on actually a collaboration with Professor Marcus Bodin and also Yunfen Zhang from the same place, from the Yale Center of Southeast University. And I'm going to talk about the rational Q systems and linear quiver gauge theories. And as the title suggests, so actually this is our work is a small addition to the famous correspondence between Bethe and Ansatz and the gauge theory. So let me remind you that the so-called Bethe gauge correspondence basically is a very surprising connection between supersymmetric field theories and quantum integrable systems. In particular, it states that the suitably of 3D n equals 2 star theories on S1 are given by solutions to the so-called Bethe-Ansatz equations. And these Bethe-Ansatz equations they arise a long time ago already in the field of integrable models. And there they describe the spectrum of some quantum integrable models like Higgsing spin chains. And therefore, like integrable experts, they have very practical experience with solving these Bethe-Ansatz equations. And then they found that actually the best way to solve these Bethe-Ansatz equations are not by attacking these equations directly, but by through a very ingenious reformulation of these equations, so-called rational Q systems.
Sorry, a quick thing. The audio for me is a little bit fuzzy. I don't know if it's the case for other people, but
yes.
Yeah. Okay. So can you change the microphone that you're using? Do you have like a because like this it's a bit.
Okay. Let me switch off and I'll restart my microphone.
Okay. Let's try this.
Hello?
Hello?
Is the sound okay now?
Oh, now it's much better.
But
Perfect.
somehow I can hear myself.
Oh, I see.
Wait.
Yeah, let's take our time.
Can you still hear me?
Yes, we hear you very well. I hear you very well.
Can you hear me?
Yes.
And the quality of the sound?
It's now slightly less, but it's not as bad as before. It's okay now.
Okay, so you can hear me clearly?
Yeah. This like this we can continue.
Okay, very good.
Perfect. All right, let's crack on. Sorry for the interruption.
It's okay. So as I was saying that experts in integrability, they told us the lesson they have for us is that in order to solve these Bethe-Ansatz equations, it's best to solve them indirectly through a rewriting of the Bethe-Ansatz equations called the so-called rational Q systems. And however, these rational Q systems, they were only written down for relatively simple Higgsing spin chains corresponding to some particular shapes of the quiver gauge theories. And so one important lesson from our work is that we generalize the construction of these so-called rational Q systems to generic spin chains, which corresponds to generic A-type quivers. And therefore, with our construction of Q systems, then you can have a very efficient way of solving the Bethe-Ansatz equations and therefore finding the suitably. And on the other hand, another lesson that we can provide from our paper is that we then, and this is the only in reverse, that we have lessons for integrability experts as well. So actually many ideas in quiver gauge theory, they can be like mirror symmetry and Higgsing mechanisms, they can be imported to integrable models where they also have interesting consequences. So now this is the outline of my talk. First, I will give a quick overview of the 3D n equals 4 theories and their quantification to, and their supersymmetric reduction to n equals 2 star theories. And then, also, of course, the corresponding Bethe and gauge correspondence. And then the third part is the core of my talk, the rational construction of rational Q systems and why they are equivalent to the Bethe equations and how to solve these Q equations, the Q systems, and why they are superior than the Bethe equations. And then if time permits, I also discuss the lessons for the integrable aspects using ideas from gauge theory. Finally, I'll conclude and present the outlook. Is everyone okay with this overview?
Yes.
Okay, so let me give some quick overview of the 3D integrable theories, because people are experts. The audience is many experts on this. So I will be rather quick. So why are we interested in 3D integrable theories? And these theories, they are interesting because first of all, they are relatively easy to understand. You have various ways from string origins to construct the theories, and people have very good understanding of the modular spaces as well as Hilbert series on the modular spaces, and also defects operators like monopole operators and vortices and etc. And there are also various ways to compute potential functions of the 3D theories. And besides, the 3D theories have interesting properties like mirror symmetry and etc. But the most important for us, these 3D theories are catch our attention because they have deep connections to quantum integrable systems. And the 3D theories that we're interested in are so-called TSUN type, and they can be constructed in type 2B superstring theory as the following. So we have a bunch of NS5 branes, D5 branes, and D3 branes. They occupy the common directions x0, 1, and 2. And then you have NS5 branes separated along the direction of x of the 6 dimensions. They occupy the dimension 3, 4, 5, but as I separated in dimension 6, and these are NS5 branes. And then in the interval between the i's and i's plus 1 NS5 branes, you have a bunch of D3 branes suspended between these NS5 branes. And you also have a bunch of D5 branes located there. They occupy the dimension 7, 8, and 9, but they're points in the directions 3, 4, and 5. And then in this construction, people know very well that there is a 3D n equals 4 theory that lives on the common direction 0, 1, and 2. In fact, this is a linear quiver theory, and with gauge nodes, these gauge nodes, and you basically at each gauge node you have UN gauge symmetry corresponds to open strings in between these D3 branes, and you also have flavor nodes MI. These basically are hypermultiplets transforming in the fundamental representation of these gauge nodes. And you also have bifundamental representations between these neighboring gauge nodes. And it is well known that this is a basic UV description of this theory. And it flows to some CFT in the infrared. And it's well known, for instance, from this paper, that if this so-called balancing condition is satisfied, then it flows to the interacting superconfort field theories. These are referred to as good theories in this paper. And these are the theories that we would be interested in. Now, so let us have some look at a bit in detail of these superconfort field theories. First of all, what are these global symmetries of the SFT? This global symmetry mainly consists of 3 parts. The first part is the R symmetry, and for the n equals 4 amount of supersymmetry, the R symmetry splits to 2 copies of SU2, and they have very nice geometrical realizations. The first copy is realized as rotation symmetry of in the direction 7, 8, and 9. So they basically rotate NS5 branes, but keep D5 branes invariant. And the second copy, SU2C, this is rotation symmetry in the direction 3, 4, and 5. And so they rotate to D5 branes. And the second part of the global symmetry is the flavor symmetries. And this is probably the simplest part of the global symmetry. And basically you have a direct product of these UMs, and then you divide out the diagonal UM component. And finally, the final component of the global symmetry is the Coulomb symmetry. So basically for each gauge component UN, and you have a topological symmetry UNJ. And this comes from basically the Hodge dual of the field strengths. And so in general, you have a product of this U1. You have U1 raised to the power of L-1. Each U1 comes from each of these gauge nodes. However, this is the symmetry. This is the global symmetry in the UV. And when you go down, when you flow to the infrared, this global symmetry may be enhanced where the so-called multiple operators, they would act as ladder operators. So this abelian symmetry may be enhanced to a non-abelian global symmetry. And to read off this non-abelian part of the global symmetry, it's actually very easy. You basically look at the gauge nodes which are balanced, which means that this balancing condition here is 0. This is called a balanced gauge node. If this gauge node is balanced, then you mark them out, and then all these gauge nodes which are marked, they form the Dinkin diagram of the non-abelian part of the Coulomb branch global symmetry in the infrared. For instance, the example here, these blue nodes, these are balanced. So you have this denote, and this tells you that you have SUL-1 non-abelian global symmetry. And then you also have another U1 from this node. These are global symmetry of the so-called field theory. And next, let us look at the deformation parameters of the superconformal field theory. First of all, for each Cartan generator of the GH, the flavor symmetry, you have a triplet of masses, and they basically are the variable scalars in the background vector multiplet associated to these Cartan generators, and they transform as a triplet in this SUC component part of the R symmetry. And actually, geometrically, they realized these three real masses, they realized the positions of D5 branes. And then because these D5 branes, they are rotated by the SU3 symmetry, which is precisely this SU2C part of the R symmetry. And similarly, for each Cartan generator of the GC, this Coulomb branch global symmetry, you also have a triplet of Fourier-Ilipoulos parameters. And then they are the verbs of the three real scalars in the background vector multiplets associated to this symmetry. And now geometrically they are realized as relative positions of neighboring NS5 branes. And because these NS5 branes are rotated by the SU3, which is nothing else but the SU2, this SU2 component of the R symmetry. Therefore, these Fourier parameters transform as a triplet of this R symmetry. Now, these T-symmetry, these 3D and cos4 theories, they are very interesting, have a very particular feature, which is that they actually, each of these linear quiver gauge theory can be uniquely described by two partitions. And these two partitions have the same number of boxes. And so how are these two partitions defined? So the first partition, the sigma, first let us look at the transpose of the partition. Then the components, the elements of the transposed partition, these are given basically by the sum of the flavor labels. And because these flavor labels, these are non-negative natural numbers. Therefore, when J increases, you can see that indeed these are non-increasing natural numbers, therefore giving you a partition. And the second partition is defined as the following. This is a bit complicated, but you can convince yourself that actually they can be written as sums of the balancing conditions. Now, for a good quiver theory, these balancing conditions, these are all non-negative natural numbers. So when I increases, these rho I also non-increasing natural numbers. Therefore, this rho I also form a partition. If the quiver theory is good, then the rho is also a partition. And physically, these two partitions, what is the meaning of these two partitions? And actually, they have a very clear physical meanings. We can write down, first of all, the brane diagram for the quiver theory, and then we move all the D5 branes to the left and keeping all the NS5 branes on the right. And then if you take into account this brane creation and annihilation mechanisms, these Hanani-Witten moves, we can see, for instance, for this SQED, and the vanilla brane diagrams like the following. And we move all these D5 branes to the left, we have this diagram. And then these rho i's nothing else but the net numbers of D3 branes ending on NS5 branes. In this example, we have two D3 branes here and one D3 brane. Therefore, the potential rho is 2,1. And the sigma j, the other partition, these are given by the net numbers of D3 branes ending on the D5 branes. For on each of the D5 branes, you have one single D3 brane. Therefore, the partition sigma is 1,1,1. And it's also very clear why the total number of boxes of the two partitions are the same, because this is given by the total number of D3 branes connecting the D5 and NS5. Now, let's go to the next section. So these are the 3D n equals 4 theories, but this is not the theory that actually we're interested in. In order to make connection with quantum integrable systems, we actually need to softly break the supersymmetry down to n equals 2 star, and also compactify the theory on S1 to get a 2D n equals 2,2 star collapse current theory. And so how do we do this? We first break the supersymmetries softly. For this purpose, we choose and preserve an n equals 2 subalgebra of the n equals 4 algebra. So how do we do this? First of all, let us recall that the asymmetry of the n equals 4 algebra has these two components, and we will denote the Coulomb generators of them to be JH3 and JC3 respectively. And then we can choose a diagonal component of this asymmetry to be the U1 asymmetry of the n equals 2 subalgebra. For instance, we can choose the plus the sum of JH and JC to be the generator of this U1R. And then from the perspective of n equals 2 subalgebra, the orthogonal current JH minus JC, this would be the generator of a non-asymmetry. This we would call U1 eta. Now it's clear that how do we softly break supersymmetry? Basically, we couple to an n equals 2 background vector multiplet U1 eta, which corresponds to this new non-asymmetry, and then we turn on the real mass. This real mass is nothing else but the value of the real scalar of this n equals 2 vector multiplet. And after doing this, because the asymmetry is reduced from 2 copies of U2 to U1, and then supersymmetry is also reduced to n equals 2. And remember that each n equals 4 vector multiplet contains 3 real masses, but after you break it down to the n equals 2, it consists of n equals to 1 n equals 2 vector multiplet and 1 n equals 2 carol. The former contains a single real scalar, and the latter contains a complex scalar. And because these flavor masses, n equals 2 flavor masses, and the phi eta plus parameters, they are values of the 3 real scalars of the background vector multiplets. And after supersymmetry breaking, they naturally split also to real and complex components. The real components would correspond to n equals 2 vector multiplets. Therefore, they're relevant to the Coulomb branch of the daughter theory. And the complex components, because they come from the carrier multiplet, now they are irrelevant for the Coulomb branch. So we'll be interested in these real components. And so here's a little summary. After supersymmetry breaking, we have these 3 components of the non-asymmetry. You have the GC and GH and GC, which is inherited from n equals 4 theory. And in addition, we have this U1 eta symmetry due to the supersymmetry breaking. And then we also have the real parameters, which come from the background vector multiplets associated to these global symmetries. And next step, we would like to compactify the 3D theory on S1 to get a 2D closed current theory. And after this compactification, then the vector components of these background vector multiplets, they would give Wilson lines along this S1, and then these Wilson lines are naturally combined with the value of the scalars into complex deformation parameters. And these are the twisted masses of the 2D effective closed current theory. And furthermore, because these Wilson lines are actually periodic, it's natural to define the exponentiated variables, which are now single-valued variables. Now, remember, now keep in mind that these y variables, these are associated to the flavor masses. These epsilon variables are associated to the real phi eta plus parameters. Finally, the q parameter is associated to the U1 eta symmetry. In addition to these deformation parameters, and we also have the Coulomb moduli. And these Coulomb moduli, these are the scalars. These are values that are the real scalars in the dynamic n equals 2 vector multiplets. Again, similarly with the background vector multiplets, you can consider the vector components of the vector multiplets, and these vectors again would wrap around the S1 to give you Wilson lines, which can be combined with these real Coulomb moduli to give you complex Coulomb moduli. And because these Wilson lines are also periodic, you can exponentiate these Coulomb moduli to get a single-valued Coulomb moduli. Now, the two-dimensional Calotte-Kahn theory after compactification is described by an effective theory in the infrared with all massive fields integrated out. In fact, if you turn on the generic twisted masses, here this twisted masses from 2D point of view includes all these parameters: the flavor masses, Biedis parameters, and U1 Edis parameter. If you turn on these variables, you turn on these parameters and make them generic. In general, the Coulomb branch would break down to actually the whole modular space of the theory would break down to isolated points, and these are the supersymmetric vector that we would like to compute. And the procedure to compute these isolated points, this supersymmetric vector, is the following. We can first of all we can keep this first keep this twisted mass off. We set them to 0. Then we still have a Coulomb branch. And then we move into the Coulomb branch of the modular space, where the gauge theory is reduced to an abelian gauge theory. Now, the field strengths of the abelian gauge symmetry, these are twisted Carroll multiplets in the 2D theory. So the dynamics of these field strengths is controlled by the effective twisted superpotential. And then you can turn on the twisted masses, after which you have a bunch of massive fields, and you have to integrate out in the infrared, and then they will give contributions to the twisted superpotential. Then you can compute the twisted superpotential, and you can try to find the minima of the superpotential, which is precisely the super vacuum. And fortunately for us, this twisted superpotential is not that difficult to compute, and because it's one loop exact by the renormalization theory. And furthermore, we know all the sources which can contribute to the twisted superpotential. There are in principle only 2 types of sources. The first source comes from 3D n equals to Carroll multiplets. And suppose you have a 3D n equals to Carroll multiplet, which becomes massive after you turn on these twisted masses. And then its contribution to the twisted superpotential is given by this L function. This L function is defined by its derivative, which is logarithm of the sinh. We're only interested in its derivative because afterwards we're going to take the derivative. We are going to solve the critical points of the twisted superpotential. And another source comes from the topological symmetry of a gauge symmetry. Suppose we have a UN gauge symmetry with a single UNJ topological symmetry, and remember that the value of the background vector multiplet of this is given by the Biedis parameters. And then this Biedis plus this Fi term would also give a contribution to the twisted superpotential, which is given by the following form. This UK, remember, are the Coulomb moduli, and this T is the Fi parameter. And then you can basically, if you understand that you only have contributions to the twisted superpotential from these 2 types of sources, then you can basically enumerate the massive Coulomb Carroll multiplets in your theory, and you also enumerate the Fi plus Fi terms in your theory. Then you collect the contributions of these things, and you can compose the total twisted superpotential. And then the super vector is given by the critical equation of this function. However, this equation is actually also corrected by quantum effects, which tells you that instead of this 0 equation, the right-hand side can be arbitrary integer number. So the true equation for the Soucy vacuum is given by the exponentiated equation. So let us look at an example of this calculation. Are there questions upon this point?
Yeah, sorry, but what about Chern-Simons contributions?
Chern-Simons contributions.
Since you have 3D n equal to theories, or?
We start from a 3D n equals 4, so there's no Chern-Simons contribution.
Oh, yeah, yeah. Okay. Thanks.
Thank you. More questions? Okay, then let me continue. Let me give you the example of the calculation of the twisted superpotential. So suppose we have a SQCD with gauge group UN and M fundamental hypermultiplets. then the twisted potential actually looks as the following. So it has three contributions. The first contribution comes from the carrots in the hypermultiplets, and because each hypermultiplet contains basically two n equals 2 carrots, they transform in respectively the fundamental and anti-fundamental representation of the gauge symmetry. Therefore, here you have this UK and minus UK. These are the Coulomb moduli. This tell you the charges of the carrots in the gauge group. And again, because these carrots, they transform in the also fundamental and fundamental representation of the flavor symmetry SUN. Therefore, you have these flavor masses with sign plus and minus. And finally, the term eta over 2. This is given by because this charge these carrots have charge +1 on the U1 eta symmetry. And the second line comes from contributions of the carrot multiplets in the n equals to vector multiplet, and because they transform in the adjoint representation of the gauge group, that's why you have the UK minus UL, and these are basically roots of the UN symmetry. And also because they have charge plus minus 2 of the U1 eta, you have this term minus eta here. Finally, this term comes from the plus term because you only have one gauge node, so you have only one Fi term. And then once you have this twisted potential, you can plug this into the exponentiated equation to write down the suitably equation. And here I give it to you. So it has basically two components. The first component is a product of all the Coulomb moduli, and the second component is a product over all the flavor masses. And you have basically one such equation for each UK for each Coulomb modulus. Now, it's very beneficial actually to rewrite this supersymmetric vacuum equation in terms of the so-called the Baxter Q function and B function. So this Q function is defined so that it vanishes when x is equal to one of the Coulomb moduli. And the B function is defined when it vanishes, so that it vanishes when x equals one of the yj. And besides, you have these superscripts. Plus means that you shift x by a q, and minus means you shift x by 1 over q. And so basically, this gives you this component, and this gives you the other component. As you see that this formulation is simpler, and besides, it's easier to generalize this formulation of the Susi-Bjerkren equation to linear quiver theory. So if you have a linear quiver theory of this type, and then the Susi-Bjerkren equation can be written down as following. You basically have one such equation for each gauge node, A from 1 to L minus 1, and also for each Coulomb modulus, K from 1 to N or NA. And here in this equation, you have basically three parts. The first part is the black one. This comes from the Coulomb moduli of the node itself. And then the red part comes from the neighboring gauge nodes. And finally, the blue component comes from the flavor node. Okay, these equations they look elegantly. Actually, they also appear as the so-called Bethe-Ansatz equations in the field of integrable systems. These are, as I said before, that they describe spectrums of the so-called XXZ Heisenberg spin chains. So basically, you have a periodic chain of spins. And then the spins transform in some SUN representation. For instance, if you look at the SQCD of this type, then it's a Susi-Bjerkren equation. Basically, it gives you the Bethe-Ansatz equations for the spin chain where each spin transforming in SU2 representation. Then the flavor node M gives you the number of sites. You have basically n spins. And then the gauge label n gives you the number of magnons. The magnon means that the number of the spins which are pointing up. For instance, these are magnons. These are anti-magnons. And besides, if you look at this kind of quivers, these are called triangular quivers. Basically, you only have one flavor node here and no flavor node afterwards. And these are called a triangular quiver. And a triangular quiver of this type, this corresponds to, you have three gauge nodes. And this corresponds to, this Susi-Bjerkren equation of this quiver theory is the Bethe-Ansatz equation of a spin chain where these spins transform in SU4 representation. Again, this n is the number of sites. And then the three nodes, because there are three types of embedding of SU2 into SU4. Now, people in the field of integral models have tried to solve these band ansatz equations for a long time, and they found that these equations are in general very difficult to solve. There are basically two types of problems. The one is theoretical, another is practical. The theoretical reason is that there are a bunch of unphysical solutions. So if you just naively solve these band ansatz equations, some of these solutions do not correspond to the spectrum of the integral model. They also are not truly the suitably that we're interested in gauge theory. And these are basically, for instance, if you have, okay, so let's say this xk, the solutions of these equations, let's call them beta roots. And then if some of these SKs, some of the beta roots are coinciding, and this is an unphysical solution. And another situation is that if these SKs, if solutions are such that the numerator and the denominator vanish simultaneously, or if they become infinite simultaneously, these are singular solutions. And some of these solutions are also unphysical. So basically, if you just solve these band ansatz equations, and you have to really be careful that some of these solutions are physical and some are not. And from a practical point of view, the band ansatz equations are difficult to solve because they are numerically unstable. So if you change the parameter slightly, the solutions might be very different. And I mean, this may not be because these solutions are truly different, but because solving them are numerically unstable. And also, these band ansatz equations are very inefficient to solve. You take a long time to solve them, even on a fast computer. So in 1997, Marble and Volley, they designed an ingenious way to rewrite these band ansatz equations into the so-called rational Q systems, and which magically can avoid all these unphysical solutions. First of all, if you try to solve this rational Q system instead of the band ansatz equations, then these unphysical solutions, they magically disappear automatically. So first of all, you don't have to worry about the second problem, the theoretical problem. And besides, these rational Q systems also are numerically stable and also more efficient to solve. In the original paper of Marble and Volley, they wrote down this rational Q system for X type of spin chain. These are basically some certain limits of XXZ spin chains. And later they were generalized to some XXZ spin chains. These are and they correspond to triangular quivers. So these are not the most generic spin chains, and because they do not correspond to the most generic quivers. And in our work, we basically give you generalization of this construction to generic A-type quivers. And this is what I'm going to present in the next part. Are there questions up to this point? Okay, now, so let me go to the second part, the next part of the, yes, please.
So the question is even before you go into what you're going now, what's the relation between the original 3D n equals 4 theory and the integrable system? Are you saying that the 3D theory n equals 4 is integrable? I understood that you did all this.
No, you have to compactify it on S1 in order to make connection with the integrable system.
So if I don't, so your point is that if I do not compactify, the compactification and all the procedure you described will generate an integrability in the system.
No, so only after you compactify it on S1, then you get an integrable system.
I see.
So basically, so actually, the original correspondence, or the original statement of the correspondence was between 2D theory, 2D gauge theory, and the integrable. So basically, the correspondence between 2D gauge theory and the X type of spin chain. Yeah. And then the 3D theory after compactify on S1. So this is basically 2D Clauss-Kahn theory. You have an infinite tower of new states. Then this gives you a correspondence with XXZ spin chain. And you can also go one step further. You can consider 4D theory compactify on torus. Then have even more states, and then this gives you a even more generic type of spin chains, XYZ spin chain.
I see.
So you must do the compactification.
Good. So this quiver you drew one page up, right? That one, yeah, that one. What's the relation between? So the relation between this one and the original 3D quiver is going through all the things you explained of the compactification, Wilson line, etc. So these numbers I see here. they are not necessarily the numbers of the 3D n equals 4 theory.
Well, you start with the 3D n equals 4 theory of this quiver type, and then you do the compactification. And then you're right. So originally in the 3D theory, you have, for instance, you have real masses and etc. And then after compactification, you have a complex mass.
Yeah. Okay. All right. Thank you.
You're welcome. So now let me present our construction of the genetic rational Q system. Remember that the 3D theories that we were interested in are uniquely described by two partitions, rho and sigma. And the rational Q system that we construct is also defined by these two partitions. So we first take one partition, say rho, and then we can use it to define a bunch of bold-faced Q functions. So how do we do this? We first construct a Young diagram with row I boxes on row I. So we have so here we have row 1 boxes on the first row. We have row 2 boxes on the second row. And then we say that we can place a bold-faced Q function at each point. For instance, at a point here, at all these points, we can place a bold-faced Q function with subscript a, s. And also demand that this bold-faced Q function is a Laurent polynomial in X. And furthermore, there's a so-called QQ relation for the bold-faced Q functions at the four corners of each box. So for instance, at this box you have 4 Q functions, and then they are related by these so-called QQ relations. And here on the left-hand side, these blue Q functions, they come from these two nodes. And then on the right-hand side, QAS and QA plus 1 S plus 1, they come from points on the orthogonal diagonal line. And again, this
the blue guys
yes?
come from the gauge node, and the red guys come from the flavor node, or is this a different color coding?
No, this has nothing to do with the previous.
Oh, okay.
So this whole diagram comes from this row partition, and this row partition, if you remember, these row i's, these are balancing conditions. Okay. And also these superscripts, the plus and minus, remind you that this means you have to shift x by either q or q inverse. So here I have a definition of a bunch of q build-faced q functions at each vertex for each point of the Young diagram, which is given by this row partition. Now I have another partition. How do we use this other partition? These other partition, if you remember that they specify especially the transpose of the partition. They specify the flavor labels. So the elements of the transpose are given by the sum of the flavor labels. And now I can use these flavor labels, or equivalently, I can use this partition sigma. I can use these flavor labels to define the boundary condition of this bold-faced Q function. What do I mean? I first say that this bold-faced Q function at the top, these are all 1. And then I say that the bold-faced Q function placed on the left boundary, they split to the Baxter's Q function. If you remember, these are defined so that it vanishes if x equals to a Coulomb moduli. And also an f function, small f function. This small f function basically contains information of the flavor labels. Here is the definition of the small f function. So if I have at a vertex A, and then A is a product, then a small f function is a product starting from A plus 1 and upwards. These B functions with subscript A plus 1 up to L minus 1. So A plus L minus 1 minus A is L minus 1, starting from A plus 1 up to L minus 1. Remember that these B functions, they are constructed so that it vanishes when x equals 1 of these flavor masses. Besides, each of these each of the factor, you have to repeat this B function by several times. For instance, when k is 1, then you don't repeat it. Basically, you have only one. You have just one copy of B A plus 1. But if k is 2, you repeat this B function by 2 times. You have A plus 1, B A plus 2, and xq shifted by one inverse 1/2, and then BA plus 2 x shifted by positive 1/2. And then when k is 3, you have 3 copies of A plus BA plus 3, and then x is shifted by this q respectively. So this is our construction of the small f function. Basically, it contains the information of the flavor nodes, which is also described by the second partition sigma. Now, let me first try to convince you that this rational Q system that I have described so far contains the same information as the Bethe equation. Suppose we have, first of all, we look at the gauge node at a minus 1 and 0, and then we look at the QQ relation associated to this box. And then this QQ relation has the following form. And then we can take x to be a Coulomb modulus xk a, and then remember that this bold-faced q comma 0 contains the Bethe q function, and it vanishes when x takes value of one of the Coulomb modulus. So this term vanishes. When this term vanishes, we don't have the left-hand side; we only have the right-hand side, and this right-hand side has the following form. And then you can assume that none of these terms vanish. Assuming that none of these terms vanish, it can be taken into the ratio form, where you have first of all you have the bold-faced q from the leftmost column. These contain the q functions, Bethe q functions that we're interested in. It also contains this bold-faced q from the second column, and these are the things which are unknown. Now, we can next thing we want to do is that we look at one node up. We look at this node, and then we look at the QQ relation coming from the box above it, and then this QQ relation has the following form. Now we're doing the following trick: we shift x to x times either x times q or x over q. If you shift x by q, then we basically place a plus sign over each of these of the bold-faced q. Then we have the first line. If we shift x by 1 over q, then we plus a minus sign, and then we get a second line. And then we set x to be one of the Coulomb modulus, and then these terms would vanish. All these red terms would vanish. Then we have only these blue component, these black components. Again, we take the ratio. We take a ratio. We get another expression of this bold-faced q function on the second column in terms of the bold-faced q function on the first column. And then we plug this into the previous equation. We get an equation of the bold-faced q function on the first column. And then we plug in the boundary condition in terms of the small f function and the Bethe q function. And we separate them into these two blocks. And you can check that this is a non-trivial statement that by our construction of the small f function, this block of small f function basically is equal to the ratio of the B function that contains the information of the Philip masses. And then we arrived at precisely the desired Bethe equations. So this is basically a derivation, an argument that indeed the rational Q system that we constructed, it contains the same information of the Bethe equations. Next thing I would like to, are there questions now in this part of the talk? Okay, next thing I would like to convince you that solving this Q systems is also, let me also present you the way to solve this the rational Q systems. How do we solve this? The basic idea is that we first solve this Bethe Q functions from the Q system, and then we found the better roots as indeed the roots of these Q functions. So we can remember that this Bethe Q function, these are defined as the following, and then we can expand it. And then these coefficients of these polynomials, these are nothing else but the symmetric polynomials of these better roots. And then let me parameterize by the CK coefficients. And if I have parameterized this Q function as the following, then this bold-faced Q function on the first column are already fixed. They are fixed in terms of these parameters. then the remaining Q functions, they can be recursively solved by the QQ relations in terms of these functions. However, in this process, you find that this remaining Q functions solved in this way, they are not necessarily Laurent polynomials. If we impose the condition that these are also Laurent polynomials, we will get a bunch of algebraic equations for this coefficient CK, and from which we can, these are called zero remainder conditions, and from these zero remainder conditions, we can solve these parameters, and then we plug them into the QA, and then solve the Bethe roots from QA. Again, let me give you an example of how this is going. So we have this Young diagram with both phase Q functions attached to each of the points. And we first look at the top row, and top row is simple. We already imposed that each of the both phase Q is 1. And then we go one row down and we look at these Q functions here. And then they are the QQ relations associated to these Q functions. These are linear because, I mean, for instance, for this box, we have relations between we have a product of this and this, but this is 1. So the original quadratic polynomials become linear polynomials. So the QQ relations of these boxes, these are linear equations. And this is a recursion relation because, for instance, this S plus 1 and S. So we can recursively solve all these both phase Q from the Q on the left boundary. And because this is linear equation, these solutions are also Laurent polynomials. Then we look at the next row. If we look at the next row, these QQ relations, they have the following form. These blue components, they come from the previous row. These are already known objects, and we can divide this term to get an expression, recursive expression of S plus 1 in terms of these S, this Q both phase Q function with subscript S. Now these blue components, these are already known, but this component, this QL minus 1 and S, this is a Laurent polynomial. So in general, the ratio on the right hand side, in general, is a rational function. It's not in general a Laurent polynomial. So if we demand that this left hand side is a Laurent polynomial, then the remainder of the division on the right hand side should be 0. This is a zero remainder condition that I was referring to. And you can repeat the procedure row by row until you reach the bottom, and you get a bunch of zero remainder conditions from which you can try to solve the coefficient C. It turns out that this way of solving Bethe roots is much more superior than solving the Bethe Ansatz equations directly. It said that unphysical solutions are automatically eliminated, and solving the Q system is also numerically stable and also much faster. And so one reason that you can already see that solving Q system is superior is more efficient than the Bethe Ansatz equation is to simply look at the fact that the symmetry of these Bethe roots is exploited in Q system. If, for instance, if you look at the back to Q equation, you find that these the Bethe roots of the same gauge node of the same A, they have the permutation symmetry. Of course, you permute these Coulomb moduli coming from the same gauge node, and this would not change this Q system. The permutation of these Coulomb moduli, these Bethe roots with fifth A, this does not change the solution to Q system because it will not change this Q function, but this would change the solutions to the Bethe Ansatz equations. So this is one of the reasons that solving the Q systems is more efficient than the Bethe Ansatz equations. Here is a demonstration of the efficiency of the solution of Q systems. Again, we just look at a simple example of the SQCD with gauge symmetry SUN and with gauge symmetry UN and flavor symmetry SUN. And we can increase, and here the second column gives the time in the unit of seconds to solve the corresponding Bethe Ansatz equations, and third column is lists the time in the unit of second to solve the responding Q systems. And you can see that for each example, it's much more efficient to solve Q systems. In this striking example, the solution of the Q systems is 900 times more efficient than the Bethe Ansatz equations. And this is only the example of SQCD. And in general, for any linear quiver, we have a construction of the Q system. So solving them is always more efficient than solving Bethe Ansatz equations. Are there questions up to this point?
Hi, Jay. Can I ask a couple of questions?
Sure.
You basically always solve it numerically in the end using recursion relations, right?
Yes. This is what we do in this paper. But okay, please continue.
Yeah, so my question is, this twisted indices has to do with black hole microstates, but it's in large N. My question basically, what's going on in large N with your method? Because Bethe Ansatz becomes thermodynamic in these limits, and we can find analytical solutions. So do you have any idea of large N?
To answer your question, I have to jump to the very end of my slide.
Okay, sorry. No, then I will wait. Okay.
But it's okay. I mean, this is what we're going to do in the future. So we basically have some idea of solving this the Q systems algebraically.
Okay, good. Then I will wait for the end. Okay. Yeah. Thanks.
Are there more questions? Okay, if not, let me jump to the next section. So in the next two sections, I'm going to actually describe how people in the field of integrability can learn something from the gauge theory. So basically, the first technique is the mirror symmetry and the second Higgsing. But the Higgsing and the mirror symmetry has more striking consequences for integrable models. So I think I will just cover this part and skip the next part. So let me remind you a little bit, because I guess the audience are now experts in this field. Let me just remember you quickly that what mirror symmetry means for the 3D theory. The mirror symmetry for the 3D and cos4 theory basically comes from exchanging in the type 2B theory, exchanging D5 and NS5 branes, keeping the D3 branes unchanged. Then if you exchange D5 and NS5, you also have to exchange the direction of 3, 4, 5, and 7, 8, 9. And then because they're rotated by these two different components of the asymmetry, this means they have to exchange the two components of the asymmetry. You also have to exchange these flavor masses and the NFI parameters, because the parameterized positions of D5 and NS5 respectively. And finally, you also change these two components of the global symmetry. And in terms of the theories which are mirror due to each other, you not only actually exchange the D5 brane and NS5 branes, you also flip the direction of the X6. Then by this you can see very easily what are the theories which are mirror due to each other. So if we look at, for instance, if we look at this simple theory, which is QED, and then the brane diagram looks at the following. If we exchange the rows of D5 and NS5, then also flip the direction of X6, and we have the other brane construction where we basically exchange the two positions rho and sigma. Remember that these are number of D3 branes attached to NS5 or D5 respectively. And therefore, two Quiver theories which are due to each other, which are mirror due, are such that the positions of the two theories are exchanged. And when you compactify the theory to an S1 and also break the parameters to n equals 2 star, and then first of all you have to exchange the flavor masses and the Fi parameters. And here in the 2D theory, and you have an exponentially complex flavor masses and Fi parameters. So we have to exchange Y, which is the exponentially complex flavor mass, and an epsilon, which is exponentially complex Fi parameters. And also because we have to exchange GH and GC, these two global symmetries, then this current of J eta has a minus sign. So we have to exchange Q with 1 over Q. This is the dictionary of the mirror theory in 3D on S1. And in order to see that what is the consequences of mirror symmetry, I mean, how can you compute something on the two sides of the mirror symmetry which are identical? Then you can compute, for instance, the so-called A and B twisted indices. And these are basically the potential function of the 3D theory on S1 times a Riemann surface of genus G. And you have to turn on a topological twist in order to preserve supersymmetry. And you have two ways of doing this: the A twist and B twist. The A twist, in the A twist, you basically demand that the diagonal component of the direct product of the Lorentz group and SU2H to be the new Lorentz group. In the B-twist, you take another component of the asymmetry and demand the diagonal component is the new Lorentz symmetry. So you have two ways of doing the topological twists to preserve supersymmetry, and then the potential functions can be computed by localization. And if you turn on generic twisted masses, then localization tells you that both of these indices actually reduces to summation of the Bethe roots. And here HA and comma B, HA and slash B, these are so-called Handel-Green operators. And these are they are different actually for the A and B twisted indices. As you can see that if you change the genus of the Riemann surface, you do nothing else but increasing the power of the Handel-Green operator here. And the mirror symmetry then dictates that for the series which are mirrored to each other, if mirrored due to each other, and then you use the dictionary of the parameters, then the A twisted indices of the one theory is equal to the B twisted index of the dual theory, and vice versa, of course. And B index equals to the index here. And here, this is a very simple example. As I said before, that the SQED of this one is mirrored due to the simple quiver here, and with some choices of the parameters, the Bethe equations or the Q systems of these two theories can be solved exactly. And then you find out, for instance, that the Handel-Green operator of the A-type of the Quiver theory is the following form, and this is the Handel-Green operator of the B-twisted index of the QED. And you see indeed that, well, first of all, both the Bethe systems, Bethe Ansatz equations of Bethe systems have three solutions, x1, 2, and 3. For each of the solutions, indeed, these Handel-Green operators are equal to each other under the dictionary of the parameters, because each of the Handel-Green operators are the same. Because each of the Handel-Green operators are the same, then naturally, as a consequence, you know that the indices A twist index is equal to the B twist index of another theory on any genus. So this is a story probably people know very well from the gauge theory point of view. Now the consequences for the quantum integrable system is that it's telling you, because the solutions of the Bethe Ansatz equations describe spectrum of these two theories. Then the consequences is that the two quantum integrable systems which are due to these two 3D theories which are mirrored to each other. These two quantum integrable systems, in general, they are very distinct theories. And then the spectra of these two theories, they are one-to-one correspondent. This is called a bispectral duality. And this is a version of bispectral duality already written down for instance, in this paper. But we can go a bit one step further. Basically, because the indices, they are identical to each other for any genus, then consequently the Handel-Green operators must also be the same to each other for any of the Bethe roots, for any of the solutions of Bethe equations. And we can check, and this quantum integrable systems, you have a lot of conservative charges, and we speculate that these Handel-Green operators are actually identified with certain conservative charges. So our conjecture is that for two quantum integrable systems, which are so-called bispectral due to each other, you have certain conservative charges which can also be identified. And finally, we also give a very easy determination of the two integrable systems which are due to each other. So it's very clear because the mirrored theories, I mean the 3D series which are mirrored to each other, they are such that the two partitions are exchanged. And now for quantum integrable systems, we can write down the Q systems which are also determined by two partitions. And then these two theories, quantum integrable systems, also be such that these two partitions associated with the Q systems should be exchanged. Let me skip this part and come to the conclusion. So basically, we have seen that the rational Q systems are more suited than actually the Bethe Ansatz equations to describe the Bethe gauge correspondence. And for a generic A-type quiver theory on S1, we give a construction of the rational Q system, which then can be used to solve the Suitably vacuum efficiently. And lessons for the experts in the integrable models is that we demonstrate how to import ideas like mirror symmetry and also Higgsing, which I do not cover here because of time constraint, and reformulate them in terms of Q systems. In particular, we give quick criteria for determining what Q systems, what integrable systems are bispectrally due to each other based on Q system. Now, our work actually opens many new directions in the future. For instance, one direction that is potentially very interesting is to solve these Q systems by an algebraic method. So there are already some methods in the field of integrable models to solve these rational Q systems algebraically. So actually, you don't have to solve these the Bethe roots individually, but you have a way to starting from the Q system, then you have a way to compute the sum over these Bethe roots, and without actually solving these Bethe roots individually. These are some algebra methods that the people in actually one of our authors, Professor Yunfeng Zhang, has devised. And we would like to apply this method also to compute the A and B twisted indices. And another direction is to look at further generalizations. For instance, we can look at orthosymplectic quivers, and they would be due to the open spin trains on the side of integral models. That is all. Thank you.
All right, thank Jay. Do we have questions?
Okay, can I ask?
Sure.
Hi, Jay. I want to come back again to the story of relevance for holography. So you were asked already about introducing Chern-Simons, and in principle, you can do it. I mean, you didn't do it as far as I understand, but you can do it, right?
Right.
It will change a little bit your balancing condition, but it's doable in principle. And it's important because, like, I don't know, the canonical example would be a BGM to consider, right? So have you thought about, will it change anything for your Q system? So basically on the level of Bethe ansatz, you should multiply your thing with x powers k, where k is in front of everything, you put x powers k, xi powers k, something like that.
You mean something like this?
Yeah. And then you multiply it with everything else. So is it implementable inside the Q system? Or?
We thought about that. I mean, you can write down the Bethe ansatz questions, but it's difficult to write down the Q systems.
I see. Okay. Yeah, that was my question, basically. Okay, thanks. Okay, and when you say about large N, you basically say about algebraic methods or what?
Well, we haven't tried that, but I mean, for any like a finite N, we can, in principle, you can try to use the algebraic method to solve it.
Okay. And in large N, there is no simplifications or anything.
Actually, I think that would be more difficult because then when N is larger, then you have more equations, then even the algebra method would be more cumbersome. So that's a difficult question.
Okay, you see, when you solve Bethe ansatz, basically you take large N, you get thermodynamic Bethe ansatz, where instead of products, you have integrals and so on. So exponent of integrals, I mean. And then you substitute your exact solution with density, with distribution. I was just thinking, I don't know, I'm not familiar very much with this rational Q system method, so there is no.
I mean, even the algebraic method or the analytical solution method that I'm referring to, this has to be done case by case for each individual N. I mean, there's no solution just as a function of N.
Okay, good. Okay, thanks. Yeah.
More questions? So you skipped over the part about the Higgsing,
yes,
because of time. But
yes,
can you very briefly explain the idea, or is it quite involved?
It's actually very simple. I mean, because people here they're experts. You are experts in the gauge theories. You know there are two types. there are two types of Higgsing, right? There are Higgs branch Higgsing where you turn on the valve of the hypers, and there's a Coulomb branch Higgsing where you turn on the valve of or vector multiplets. And in Coulomb branch Higgsing, basically, in Coulomb branch Higgsing, you keep the, I mean, you can change, you will change the flavor labels. The flavor symmetry will be changed, but the balancing conditions are never changed. So then, because the balancing condition gives you one partition and the flavor labels give another partition, so you know that one partition is changed and the other partition is not. And then, so then, I mean, from the integral model point of view, you also have a flow of integral models which are related by this Higgs branch Higgsing, and along the flow you would keep one partition and modify the other partition. Actually, because the number of boxes is unchanged, and you move the boxes around to go down the flow of this Higgsing. And for the Coulomb branch Higgsing, then because you just changed the rank of gauge groups, and then flavor labels are not changed, but you would change the balancing condition. Now you flip the rows of these effects on these two partitions. You keep the partition sigma unchanged, but you change the partition row. And then the same story here. You have a flow of integral models, and then along the flow, this row partition is changed to where you move around these boxes, but you keep the other partition unchanged. So this is two types of very interesting flows of integral persistence, which are surprising for them.
Mm-hmm. Okay, and so what's the relation between the integrable system? Is it also a Higgs mechanism in 2D?
It's a way of sort of like freezing these so-called Bethe roots, and so that so that you can actually relate the Bethe equations. You can relate to the spectrum. I mean, because these Bethe roots are the spectrum of the integrable system, then you can freeze some of the spectrum to keep them not unchanging. Then you see how this remaining, I mean, how this remaining Bethe roots should be governed by the Bethe equations of the new system. Actually, there's a very nice picture for the Higgs branch Higgsing in the spin chain. So let me look at the simple example of SQCD, and then the Higgs branch Higgsing. If you do this one step, and then you reduce this rank of the gauge group by 1, and then reduce the flavor label by 2. Right, this is a well-known Higgs branch Higgsing, and
sure.
And the spin chain that associated to this is that you have m spins. Then you have n number of spins which are pointing up. These are n magnons. And if you do the Higgsing of this type, then for one magnon, the potential between two sides becomes so large that it's virtually trapped inside. And for the other magnons, they do not feel anything when they pass through these two sides. Therefore, effectively, you can remove this one magnon, which is trapped, and you can remove also these two sides because they have no effect on the other magnons. So this is a very beautiful picture of the Higgs branch Higgsing on the spin chain.
Very nice. Thank you. More questions? Okay, then let's thank Jay again.
Thank you again for a very nice discussion and for the invitation.
Recording.